Hiya there, everyone. I hope you're all doing well. We're going to be looking at question 25 on our 2010 Pascal paper. 6 soccer teams are competing in a tournament in Waterloo. Every team is to play 3 games, and each against a different team. Note that not every pair of teams plays a game together. That's true. If I've got A, B, C, D, E, and F, A only playing 3 games means that I could have something like AB, AC, and AD, but they're never going to play E because they're restricted to only having 3 games. Okay? So Judine is in charge of pairing up the teams to create a schedule of games that will be played. Ignoring the order and times of the game, how many different schedules are possible? So if we don't care about the order and the times of the games, then it really just matters what pairs are playing off against each other. That's what we're after here. So what we're really asking is, how many ways can I pair up the teams so that each team plays 3 games? And that's the challenge. And I've got all multiples of 10, which really strikes me. I wouldn't have thought that would be something to deal with. Okay. So what can we do? We definitely don't want, with the smallest number being 60 here, we definitely don't want to just start trying to write out possibilities. So we could analyze the situation in some way, but I think it might be a good idea to start this question off by looking at maybe a smaller case. I'm not entirely sure what the best thing to do would be. Maybe look at a smaller case with only 5 teams, or maybe 4 teams, and each team plays twice. Ugh. D comes after C, you silly, silly man. And each team plays a total of 2 games against different teams. So we could have A, B, and AC. And those are the 2 games for A. Now B needs another game. D has no games, so I might do B, D, and C, D. And now B has its 2 games, C has its 2 games. Or I suppose I could have A, B, A, D, and then B, C, D, C. And these are different things because A is being paired up with different teams. So I think 3 schedules if I've got 4 teams and I'm pairing them up with, by 2s. Honestly, looking at the smaller case here didn't exactly help or illuminate any techniques. Now I could try another small case, maybe 5 with 2, or maybe 5 with 3. I don't want to do 4 with 3 because A will just play every other team, and B will play every other team, and C will play every other team. What to do? I'm going to make a little hexagon with my teams. A, B, C, D, E, and F. And I'm going to draw in some lines, and a line will mean those teams play together. So maybe AB, AC, and AD. Now when it comes to A, how many choices of line do I have? Well, I've got 5 teams to choose from. I need to choose 3 of them to play with A. Once I've done that, I was going to say then you move on to B, but what if we're looking at a scenario where A isn't facing B? So maybe move to the next team around the way and say, all right, that team has to then pair up with 3. It's interesting. I'm not seeing a good, because it's entirely possible that I make these choices. Like C can't play A, obviously, because that's already taken. But I worry that if I do something like that, if I just go back to my small case and I'm just, blindly choosing things, I could have A and B play and A and C fight. But when I go to B and choose what it does, I could choose B and C and D, and this is, well, actually I wouldn't be able to choose C and D because that would already be chosen. And then now A, B, and C, they each have their 2 games, and D hasn't played anyone. So we've got a bit of a problem. We can't just be choosing things around a hexagon. Okay, so that's out. I'm just trying to avoid doing casework, and I feel like it's going to devolve into me doing casework. Is there another way to think about this? 6 friends at a party, each person shakes hands with someone else, with 3 other people. The problem is sort of the choice. I think that's the issue. Could I do something like A here and F here, and then everybody in the... No, because what if A and F need to play each other? I'm going to go back and reread the question just to make sure. Just pairing up teams. Each team is to play 3 games, each against a different team. Pairing up the teams, create a schedule of games that will be played, so we just care about the pairs. Okay. Well, maybe we do look at the smaller case with just 5. I can have something like A, B, A, C, A, D. Then who's E going to play? E can't play A, so E has to play B, C, and D. Now, B's other play could be against C, and that would be C's other play, but who's D going to play with? This doesn't work out. You can't do 5 people and 3 games, or 5 teams and 3 games each. Interesting. Why? Well, I know why, because D gets left out in the cold, but why should that be the case? So, each team, we've got 5 teams, they each play 3 games, and so we get 5 times 3 sort of A, B, but this is also counting B playing A, and so each of those is counted twice, and so we'd need 7.5 games, which we can't possibly have. So that's, but we could have 6 times 3 over 2, and that would be 9 games. So 9 games will end up being played in this way. Okay. So, looking for 9 games now. What could we have realistically? We could have. I'm going to start off every time. I'm going to start off with who A plays against. Now I could have A play against B, C, and D. I could have E play against B, C, and D with no overlaps whatsoever, and F play against B, C, and D. That's certainly possible, but it's not necessarily guaranteed that just because A plays against 3 teams, that another team will play against those 3 teams. Now, if another team does play against those 3 teams, like we just call that team E, and there's a leftover team F who will also have to play against those 3 teams. But this is not a guarantee. We could have A play B, we could have A play C, and we could have A play D. And then B could play against one of the other teams that A plays against. C, for example. And maybe B plays against the other teams that aren't present. So, I guess what we're saying is how much interplay is there between the teams that A plays against? So in my first example, up here, B doesn't face none of the teams that A plays face each other. But now we've got some of the teams that A plays against facing each other. We've got one pair. So I suspect that this will be a case, and then maybe B can play the other two, and that's a third case, and that's so we'll go from there. But can we fill this out? Oh wait, no. B doesn't have 3 games. It would just have 2 games because it's already got 1 against A here. So BC and BE are a thing. So that covers 2 of C's games. Now I guess we have a choice. Could C play against D? I don't see why not. So let's try that. So C plays against D. That's all of C's games. All of B's games are done. E still needs 2 games. D needs a game. But F isn't playing anyone. We've sort of waited too long to introduce F. So is there a way to... have I exhausted it, or can I have C and D play each other? So C is off the table. So A is done, B is done, C is done. D has 2 of them. E has 1 of them. F has nothing. So we've got 6 games. There's 3 remaining games because we have to have a total of 9 games. F has to play in all of them. E needs 2 more games, and so we'd have E play F. So yeah, this definitely can't work. So C can't play D for its other game. So C's got to play a new one. C either has to play E or F, because it can't play D. So C, D, E. So could C play E? Well, then E's got 2 of its games done, D's got 1, F still has 0, and C's all... It's the exact same thing, just with some of the numbers in reverse. So, no, C can't play E. C would have to play F. So there's C done, and then we've got 1, 1, 1. So we just finish this off with D playing E, D playing F, and F playing E. Okay, so that's one way to do it. All right, and yes, that is definitely... So what I'm worried about is the cases that I figure out are somehow the same cases, but with the letters renumbered. So in this one, nothing that any team plays amongst itself now, but with this one down here, there is something that A plays, or there are 2 teams that A plays that play amongst themselves. And I think this is the only possibility. A, B, C, and D. Could I have B, C, and B, D? I feel like I did this a little while ago, but I can't remember. So A would be satisfied, B would be satisfied, C would have 2 games, D would have 2 games, E would have nothing, F would have nothing. So I could... No, I'm gonna have something left. So that would satisfy C. That would satisfy F, but then E, F, and E, F need to be done. There's too many games for E and F. So yeah, that definitely... So I can't have the teams of A play amongst themselves any more than that. Okay. So I think these are my only possibilities. The teams that A plays do not play amongst themselves. Or the teams that A plays, one pair plays amongst themselves. I think that's it. And everything else is impossible except just re-lettering things. So maybe not Team A, but Team B, the 3 that Team B plays, play amongst themselves. And, yeah. Okay. So I think these are the only possibilities. Now, how can I do the re-lettering? Okay, so that's going to tell me how many cases I have. So if I'm in the first case there's no overlap, or sorry, no interplay, let's say. Between any opponents. Of a team. So what I'm saying here, A's opponents don't play amongst themselves. There's not even a single game between any of them. So that means no matter what team I pick, and there's 6 choices for A, there's 5 choices for B, 4 for C, and 3 for D. But what I really am doing is picking 3 out of the other 5 teams. So when I see A, I'm picking 3 out of the other 5. Now that can be done in 5 choose 3, or 5 factorial over 2 factorial, 3 factorial. And if you're not familiar, factorials just mean n times n minus 1 all the way down to times 2 times 1. Just count down but multiply all the numbers. But this is 10. This is 10 ways. You could count it out if you wanted to. So I pick a team, and I've got 10 choices for the way I pick its opponents. But as soon as I do that, everything else falls into place. The other 2 teams that have not even been mentioned in any matches must play those same 3 teams. So I think there's 10 ways to do this. 10 for that case. And maybe there's 50 or 60. I would guess it's maybe 60 ways to do the other thing. So we'll come back to this. I'm pretty sure we've got it right there. And now if I talk about A, so I pick a team, and then I pick 10 choices. Now, back here, was there a need to choose A? I think maybe it's. I don't think it's 5 choose 3. I think that's wrong. I think it's 6 choose 3. Choose the 3 teams that will never face each other, and they must be opponents to the other 3 teams. So, yeah. So that'd be 6 factorial over 3 factorial, 3 factorial, and that'll be 20. So I think there's 20 ways to do this. It seems a little too high, but choosing AEF would be the same as choosing BCD, so I got to divide by 2, and so then that would be 10 again. Okay. I don't know what's with me with these Part C. I feel like the Part C on this Pascal, each Part C question is taking me longer than it should, and I don't like that. Maybe I'm just having an off day. Everyone has off days. So A, C, D, and then we have a choice as to who faces each other. But then after that, everything else is determined? Well, no, we had a choice as to what the other one B plays is. And C has to play F, D has to play E and F. So I pick a team. Its players play amongst themselves. Now, who does F play? F plays C, F plays E, and F plays D. Do C, E, and D play amongst themselves? E and D do. C and E don't, and C and D don't. So here's another sort of symmetry. I could look at it from A's perspective, or I could look at it from F's perspective. Or could I look at it from E's perspective? E plays against B, D, and F. B and D don't play, B and F don't play, and D and F do play. Oh, the plot thickens. How about B? From B's perspective, we've got BA, BC, and BE, and A and C play. So no matter who I'm looking at, no matter what team I pick, two of its opponents play each other. Because D plays A, E, and F, and E and F play each other. Okay. So it doesn't matter which team I'm looking at. So pick a team. 6 choices for the team, but I'll divide by that a little later. And I pick 3 of its opponents. So I pick its 3 opponents. So Team A, and then out of the 5 remaining teams, we've got 10 choices. So that's 6 times 10 here. And then I choose 2 of those 3 to face each other, and the rest follows immediately from there. Right? So I say A is playing B, C, and D, as opposed to E is playing B, C, and D. Okay. The trick here is the counting argument. I got to make sure I'm counting it right. So 6 teams, I choose 3 of them. That's my B, C, and D. I choose one of the 3 remaining teams. He's going to play each of them. I choose 3 out of the 2 teams I chose. They play each other. So here I'm picking B, C, and D. Here I pick A out of the remaining A, E, and F. And that tells me, okay, we'll do A, B, A, C, and A, D. And then out of B, C, and D, I pick 2 of them to play each other. And so this is 20, this is 3, this is another 3. So that would be 180. I feel like that's too much. Is 190 a possibility? No, it's not. Okay. I feel like I'm going to have to divide by 2 or something later. Anyway, so as soon as I choose BC, that forces D to play E and F. E and F will have to play against each other, and then I've got a choice of 2 as to who B plays. Does B play E or does B play F? And C will play the other. So this expression, which then becomes 360, which is a upsettingly big number, is the number of ways that this can go down. But I feel like I can divide by some arrangement of these numbers. I feel like I could divide by 6 or something. Because I think there's a way to get the same outcome. I feel like there's another choice I can make to get A, B, C, and D. So what if I chose... So how many ways can I get this same end result? I could focus on what... I could say, well, I could choose C, A, and E. So that's one of my 6 out of 3 choices. Choose B to play each of them. And then... So I feel like as long as I focus on the right letter, I can make what I want to have happen. And that would be 6 choices, so I divide by 6, and then I'd get 60 added to the previous 10, and that'd be 70. So I think 70 is the answer. But let's finish my thought off. So I choose C, A, and E. I choose B. Then I choose A and C to face each other. And then I choose A to face D, and C will face F out of the remaining ones, and that forces everything else to go down. So I do get the same outcome by making similar looking choices. So there's some repetition here. So it's all based on which letter I pick. So here I pick 3 letters, and then I choose A to face them. But if I choose a different 3 letters and choose B to face them, I can get the same outcome. I don't want that to happen, so let's let Team A be fixed. So that way, when I'm choosing, I'll choose 5 out of 3 teams to face A. Then there's no choice here out of what remaining team to play. Then I choose 3 out of 2 of them to face each other, and 2 choices for the remaining teams to play themselves. This fixes A. This fixes A, B, C, or A, B, A, C, and A, D. It's always going to be A here, and we'll have X, Y, Z. It'll always be choosing an X or a Y to play. And then the choice of, is X playing against U or is X playing against V? Right? And then the remaining. I feel like that's it. So that's 10, 2, 3, and 2, and that would be 60. 60 plus 10 is a total of 70. So 10 from the very, very simple case, plus 60 from this more complicated case, 70 ways that she can do this. So I think E is the answer, although I am a little hesitant. So I'm going to stick around. I'm pretty sure E is the answer, and you're welcome to look up Waterloo's solutions. They're all nice and neat and typed, but don't always explain their reasoning. I just want to make sure that if fixing A solves the problem, and I think it's got to, otherwise the numbers are getting too small. So I fix A. Is there another way I can get this same outcome? Well, if A is fixed, then it's got to be B, C, and D. So only one of these choices here will give this. Only one of these choices here will give the B-C fight. And only one of these choices here will give B-E. So, yes, I am satisfied that it is 60. And let's go back and double check, but I'm pretty sure that the 10 is what I'm happy with. So I just, again, I could just say, well, we're gonna figure out who A fights, or who A plays against. I keep saying fights. I think 5 choose 3 ways to pick who A plays against, and A is just some fixed choice that we're given, and that fills the rest of it all in. There's only one way to do this, and there's only one way to pick these numbers that gives us those A's. Yeah, so 10, 60, 70, okay. Counting arguments can be fun. They can also be sort of tedious, but I think I managed to work my way through it. Now, this video has probably been kind of long, but you wouldn't necessarily have been explaining your reasoning to everyone. I say that every once in a while. I say that whenever I feel like I did a long video. But yeah, no, it was an interesting question. I'd certainly like to see it generalized. Is there a way to know? Is there a nice expression for if I've got 20 teams and I want each one to face 8 other teams? Is there a nice way to do that? I think I'm going to go look that stuff up, and if you're curious, you're welcome to look that stuff up as well. It's always really nice when you get a math problem that makes you think after it's done. And so that's what I'm going to go take a look at. Now, that finishes off the Pascal. Up next week will be the Fryer from 2010. And then after that, we'll be back to multiple choice contests with the 2010 Kaylee. So thank you guys so much for watching. Feel free to like or leave a comment or any of that sort of thing. And I will see you for more math in whatever video you watch next. Take care.